In this exercise, we're going to learn how to do calculations with respect to the Poisson distribution in Stata. The example we're going to look at is the example of an ecological cancer study using data from the United States. In the United States, there's big cancer registry databases where the observed number of cancer cases within a geographical unit are recorded. So we have the observed number of cancer cases within a census tract. And then what we're going to do is we have the number of people living within each census tract from the U.S. Census. So we can use the population data and known breast cancer incidence rates to calculate the expected number of breast cancer cases within a census tract. And then we can compare the observed and expected number of cases to see if we're observing excess cases within any given census tracts. So read through that example on the website, and now we're going to go ahead and jump into the actual data example. The data we're looking at is breast cancer incidence data for the African American female population in the census tract from Los Angeles County, California. And you can see in this table we've broken it down by age groups so that you can sort of see how the standardization procedure took place. But what we're really interested in is this total column. We're interested in the total number of observed breast cancer cases, and we're interested in comparing that observed to the expected number of cases. And you can see to calculate the expected cases, we use the population and the cancer rate per 1,000 person years. So we just use these two columns in standardization to calculate the expected cancer rates. So what we're going to do is we take the observed number of breast cancer cases and we model that using the Poisson distribution with mean equal to the expected number of cases. So essentially what I have is y is modeled using the Poisson distribution with mean equal to 1.962. And then when I go out and I look at my population in this census tract, I see that y, what we observe, is y equals 0. So in census tract 1, using the model, y is Poisson distributed with mean 1.962, what is the expected number of women with breast cancer in the census tract? We know that based on the Poisson distribution that the expected number is just equal to the mean. So the answer is the expected value of y is equal to 1.962. The next question asks us, what is the typical departure of the number of women with breast cancer from this mean number? So what that's asking is, what's the standard deviation of y? The Poisson distribution has the property that the mean is equal to the variance. So the mean equals the variance of y. Therefore, we know that the variance of y is equal to 1.962, and consequently, the standard deviation of y is just going to be equal to the square root of the variance. I plug that into a calculator, and I can find that the standard deviation of y is equal to about 1.4. The next question asks us, would the Poisson distribution provide an appropriate model for these data? So we know that the Poisson distribution is usually used with count data. It's usually a reasonable distribution to use. However, we can't really assess any more information about whether the Poisson model fits this data really well without more data on the census tract. So given that we have count data, it's probably going to be okay. But in practice, we really use more rigorous model diagnostics to assess whether the Poisson distribution provides a good fit. Now let's go ahead and do some probability calculations. We want to know, what is the probability that exactly 0 women develop breast cancer in census tract 1? So remember, we're modeling that Poisson distribution with mean 1.962. And we're going to use the formula for this calculation. So the probability that y is equal to 0 equal to e to the negative mu, which is our mean, times mu raised to the y divided by y factorial, where I'm calling mu this 1.962. So I can plug in my numbers, and it ends up being a simple calculation. It's e to the negative 1.962, because this guy is equal to 1, this guy is equal to 1. Plugging that into a calculator, the probability of observing exactly 0 cases is about 0.141, so 14.1%. Now let's move on. So before we looked at just one random census tract in LA County. Now we're going to move on to a different census tract, Census Tract 2. And in the previous census tract, it had about the same population. Census Tract 1 had a population of 1190. This one has a population of 1184. However, in this census tract, we observe 5 breast cancer cases. Even though when we calculate the expected number of cases for this census tract, it's only 1.78, so it's very close to the expected number from the previous census tract, but we're observing way more census tracts. So we want to see, is something weird going on here? What's the probability of observing 5 or more breast cancer cases? Now, to calculate the probability that at least 5 incident breast cancer cases are observed in this population, we would need to calculate the probability that y is greater than or equal to 5. This is also equal to 1 minus the probability that y is less than 5. So we could just sum over, the probability that y is equal to I for I equals 0 to 4. But this is going to take us a while. This is going to take a lot of calculator work. So it would be better if we just went ahead and did these calculations in Stata. So Stata has 3 commands for calculating Poisson probabilities that are very similar to the binomial commands that we saw. It has a Poisson P command that returns really the probability that y is equal to little y, or to use notation consistent with Stata, they're saying x is Poisson distributed with mean equal to m, and we're looking at k successes. So really, if I wanted to use consistent notation, this is the probability that x is equal to k. Now the Poisson returns the probability of observing 4k or fewer successes. So what does that mean? It really is returning the probability that x is less than or equal to k. And last, we have Poisson tail, which returns the probability that x is greater than or equal to k. So using these 3 commands, we can now do some calculations with the Poisson distribution. At this point, go ahead and open up Stata on your computer and we'll get started. We want to do 3 calculations. We're going to calculate the probability that y is equal to 5, the probability that y is greater than or equal to 5, and then we're also going to calculate the probability that y is less than 4 to give us a different way to calculate this probability. So let's see how to do that in Stata really quickly. To calculate the probability that y is equal to 5, we're going to use the Poisson P command. And we're interested in making inference for Census Tract 2 now. We saw that the mean in Census Tract 2 was 1.781. So I type my mean in first, and then next I'm interested in the probability that it's exactly equal to 5. I perform that calculation and I find that the answer is about 2.5%. So the probability that we observe exactly 5 breast cancer cases in Census Tract 2 is 0.025. Next, we're really more interested in the probability that we observe at least 5 women that have breast cancer in Census Tract 2, because this tells us how extreme is that observation that we're observing. Is it probable that we would observe 5 or more cases or not? So to do that calculation, we can say display, and we're going to use the Poisson tail command. The mean is 1.781, and we're interested in at least 5 cases. And we find that the probability of observing 5 or more breast cancer cases is equal to about 0.35. I could perform the exact same calculation using the Poisson command if I did 1 minus Poisson. And so in this case, I would need to calculate the probability of observing less than or equal to 4 breast cancer cases, or strictly less than 5. It's the same thing. So we get the exact same result using Poisson tail or 1 minus Poisson in this example. So just thinking back to recap on what we've learned in this module, we learned that for Census Tract 1, the probability of observing 0 breast cancer cases was equal to about 14%, so 0.14. Now, Census Tract 2, the probability of observing, let's subscript this with a 1. So the probability of observing greater than or equal to 5 breast cancer cases was about 0.035. So in Census Tract 1, observing 0 breast cancer cases, it's not that rare an event. We see it about 14% of the time. We would expect to see it about 14% of the time. In Census Tract 2, we would expect to observe greater than or equal to 5 breast cancer cases only about 3.5% of the time. Now, what's the takeaway message here? We've seen that Census Tracts 1 and 2 are similar in population size, and so they have similar expected breast cancer case counts. However, in Census Tract 1, we observed no cases. In Tract 2, we observed 5 cases. Using the Poisson distribution, we calculated the probability of observing events as extreme as 0 or 5. But then you have to keep in mind that there are about 2,000 total census tracts in LA County, and we've only looked at 2 of those tracts. Therefore, we expect to see some variability in these observations, and we would expect to see some very extreme observations just by chance and by the nature of random variability. However, we could also incorporate ecological covariates into our analysis, such as median household income or land use data, to try to explain some of the differences between the observed and expected breast cancer rates.